Okay, so I guess we'll just get started. So we've gathered here today to kind of host a panel on deep learning compilers. As AI workloads have grown to dominate the industry, there's kind of been a growing need for compilers to accelerate the efficient execution of these workloads. Today, for your education and hopefully some entertainment, we've gathered several leaders in ML compilers from across industry and academia to answer your questions. So I'm going to just give intros for all of you briefly, if you guys don't mind. I just took this from your bios on the website. So we have Peng, all the way on the left, who's the engineering manager of the PyTorch compiler team at Meta. Dr. Wu spent over a decade at IBM Research working on many aspects of programming synthesis. She holds a PhD in computer science from the University of Illinois Urbana-Champaign. We have Phil Tillet, who began working on GPUs in 2011 as a contributor to the Vienna CL library. He joined OpenAI full-time in 2020 to work on Triton. Yeah, that's an introduction for Phil today. You guys wrote a lot in your bios. And we have Mikhail Zolotukhin, who is an open source contributor with contributions ranging from GCC and LLVM to PyTorch. Currently, he is at Modular, leading a team working on integration of Modular's inference stack with PyTorch. We have Jacques. Hopefully I didn't butcher that. A lead of the ML compiler systems research team at Google DeepMind. In this role, he focuses on accelerating and simplifying machine learning for high-performance model deployment across various architectures. Jacques has a PhD from Purdue University, where he focused on runtimes for heterogeneous platforms. We have Tianqi Chen, who's currently an assistant professor at the machine learning department and computer science department of Carnegie Mellon. He has created many major learning systems that are widely adopted, like XGBoost, TVM, and MLC LLM. And finally, we have Jason Ansel, a research scientist at MetaAI and a technical lead for PyTorch compilers. He started the Torch Dynamo and TorchInductor projects, which bring flexible graph capture and a high-performance compiler to PyTorch 2. Okay, so now that we have the intros out of the way, my first question is that you guys have a wide variety of backgrounds and experiences, but all of you guys have kind of ended up here on this panel for ML compilers. So can we kind of go down the line a little bit and talk about how you guys ended up here working on ML compilers and why you guys decided to work on this problem? I guess, Jason, we can start with you.
Yeah, so I did my PhD a long time ago now in compilers, and basically what I was doing is I was using machine learning to make compilers better, and this was before neural networks at all, and so I really fell in love with compilers back then, and when I started working on PyTorch about 5 years ago, it was really a return to that, only rather than using machine learning to make compilers better, now I'm using compilers to make machine learning better, and I think that's really my passion.
Tianqi?
Yeah, so I started my career as a machine learning researcher and doing machine learning, and then I still remember at that time point, it was before deep learning. I was spending 1 year hacking CUDA code just to make one model working. That was a fun memory, and then started to work on machine learning frameworks. At that time point, I found it's really time-consuming to build all those things, so that's why I started working on ML compiler. Yeah.
Jacques?
Yeah, so I mean, funny enough, I think technically I sort of started in natural language processing for a little bit. I did my PhD in heterogeneous runtimes and runtime scheduling and whatnot, and it just ended up that I kept on building things that kept on looking like compilers, except I never wanted to work on a compiler because it seemed like a hell of a lot of work to get a little performance out. But it was such a fun mathematical area, graph theory being awesome, that I was sucked in, and then when I joined Google, there was just a lot of fun projects. I was sitting next to the TPU team, up co-design, and we just built a compiler, and I got into it.
Yeah. I think a lot of projects end up being compilers when you don't expect them to. Mikhail?
Yeah, so I started my career with traditional compilers, with GCC LLVM, but then there was a surge of ML, and I felt that it's probably one of the most impactful areas that has a profound impact on all of our lives, and I wanted to participate in that, so I started working on PyTorch, and this is how I ended up in machine learning space. I tried to use my compiler experience, so that's how I ended up in machine learning compilers specifically.
Cool. Phil?
Yeah, so my background is in GPU programming. So during my PhD, I wrote GPU code for matrix multiplications, and then I wrote abstraction for it and code generator for it. At some point, I realized I'm a compiler, and I should write one instead. So that's what I did.
Cool. Peng?
Yeah, I probably have the longest career among all the panels. So I started with a PhD, and my PhD thesis was on automatically parallelizing Java. So I have always been a compiler person, and I always struggle when I try to explain to other people what I do. There's never a good demo to show. It's like a command line and shows back in numbers. And finally, I felt like with PyTorch compiler, I indeed get to do something really cool and can talk about users and product. Yeah, so that's my journey.
Thank you. So for me personally, one of the interesting changes over the past 5 years has kind of been the significant consolidation of ML architectures, particularly with transformers. And so to ask a maybe somewhat adversarial question to this panel of compiler experts, what is the point of ML compilers in a world where we're only going to run one architecture? Like if I'm the person responsible for kind of optimizing a transformer to run efficiently, why should I use a compiler as opposed to just running things by hand? I think people can just go if you want to go first, or anybody who wants to answer this question can go.
Well, then I'll go. I mean, I think it's a great question because I mean, like, it is actually funny. I mean, like, one of the reasons you build compilers is for generality, right? You're able to cover a large amount of space. But if everything looks exactly the same, then why?
Yeah.
So I mean, I think it's actually been a lot of fun with the different backends and hardware, because hardware generations still keeps on changing. The amount of different variants we have keep on changing. The quantization is insane. The amount of variants produced, sparsity is insane. And actually, one of the things Tianqi mentioned with respect to we're not actually building one compiler. I was thinking as he mentioned this, I think probably 3 or 4 different compilers arose in the last 2 months internally, because it is almost, I like to phrase it these days as deployment optimization. It's for a specific platform, different configurations and whatnot. I also struggle with good demos, command line. Oh, this is beautiful. Doesn't work on most people, but I think that is actually one of the reasons where it is focused on exploring the base for different architectures.
Yeah.
And honestly, the variety is so high that it requires customization.
So even with a single model architecture, you still have a lot of variety in how it's deployed, how it's run.
Oh yeah, some of these models we call it llama. Then it's oh wait, actually, you know what? There's 50 different variants of this. But it's the same name, but yeah.
Cool. Peng?
I just want to show attention is all you need, and then there are all these variations across time zone, across different platform and deployment. So the history is repeating itself.
Yeah.
I would like to make a maybe controversial take on this. So
okay.
I do agree with your probably a little trolly statement that compilers are not needed anymore.
Okay.
I do agree with this. I think you still need libraries though. And usually, I heard in almost all the talks, in some of the talks specifically, the phrase fighting against the compiler.
Yeah.
So it doesn't really help. You try to move it from your way. And I think you still want flexibility, but compiler is not the only way to achieve it. So let's say if you talk about attention,
yeah.
You don't really need, compiler is not the only way to be able to generate several versions of optimized attention, even though it will participate at some point,
okay.
For sure. But you don't need to be super smart that generates it ahead of time for you.
I see. So it's you I guess need to be a lot less general, or you don't need to be as general with the compilers that we have today. Or I think maybe your point is that even if you compilers you view compilers more of as a tool for building libraries, even if you're only running a couple of models.
Exactly. Yeah, I see compiler as a tool. We have an expertise who sits in the brains of kernel developers, and you want to scale it as much as you can. Compiler is one way to do it, but it's not the only way.
Yeah. Anybody else want to have a?
Yeah, I can add more. So
okay.
I have 2 answers to this. First of all, having an ML compiler solution is the only way that our team is able to run on browser, mobile phones, and all the other things. So
okay.
I cannot think of another way
so
to do that.
heterogeneous hardware.
Yeah.
It's
And another answer is that I would think compiler is fundamentally it's way to transform your program, right? Just like autograph. So I think it's a different way, it's a different methodology to write your program. Like normally we are getting used to writing programs by composing libraries, right? That's like one way to composing them. But then compiler provides this tool to take the entire program and transform in different ways. So if you can do that productively and not having to spend a lot of time building that, then it's still going to be a very useful way to in your workflow. Yeah.
So I guess for you, you think it's more about like building tools to accelerate like the optimization.
That's right.
I still have my fingers crossed that there's going to be innovations in model architecture. Like I haven't given up on that, and I think obviously like if there's only one model, then you don't need a compiler.
Yeah.
But there's been periods of time. Like there was a long time where we're like everything image processing was a convnet, and back then someone might have predicted that just like convolutions will rule the world for image processing, and we're learning that that's not true. And so I'm hoping that some clever researcher maybe in the audience here will come up with something to that is new and novel.
Yeah.
I think we need a compiler somewhere, right? So nobody writes assembly. So then the question is, what's the definition of an ML compiler?
Yeah.
Is Triton an ML compiler? I don't know.
Yeah.
Maybe at some point you go at a level of abstraction where you think it's ML, but I think if architecture changes, I think just having something like inductor can allow you to adapt to architecture, like Jason mentioned. And if you go at a lower level below than that, then maybe it's not a compiler anymore, an ML compiler anymore.
Yeah, makes sense. All right. So maybe to kind of follow up on that, like I think one of the points there is that like what a ML compiler is actually quite like ill-defined. Like even up on the stage, like Triton is a very different kind of compiler compared to like TorchInductor. Or I guess like Mojo, which is a whole separate language. So maybe I think to you guys, what ML compiler project would you like somebody else to build, unrelated to your project? So you can't say like a TorchInductor backend, not allowed. I guess you want to go first?
Sure. Yeah. So I'm going to go for a deep cut here. So there's I think like 10 or 15 years ago there was this project from Stanford called Stoke. And if you haven't heard of this before, it's basically the idea is called a super optimizer.
Yeah.
And you take in the assembly code for your x86 program, and through stochastic search and SAT solvers, you're basically like approximating an exhaustive search to find like the very best assembly instructions.
Yeah.
And this work, there was a bunch of like flurry of work around super optimizers about 10 years ago, but I haven't really seen GPU super optimizers.
Yeah.
And I think like one of the really interesting things about this is it can take even handwritten assembly kernels and potentially make them better.
Yeah.
And there's like a really small number of kernels in ML which can often dominate workloads.
Yeah.
And throwing days or months of compute time into trying to super optimize the assembly of those would be really amazing. So I'd love to see Stoke for GPUs.
Yeah, kind of dealing with the PTXAS, which I'm sure many of you on the stage have struggled with. Okay, Tianqi?
Yeah, I would say at some point I still love to automate all these mappings to the hardware, right? Especially the tensor core and DMA engine and so on. Right now, still all of these are quite manual.
Yeah.
And I feel like if we can automate a lot of that, maybe with machine learning or language models or other things, that would be awesome. Yeah.
I guess this is kind of like what TVM kind of previously, like maybe initially, kind of what you wanted to work on. But I guess like now it's like maybe a different focus, and you kind of still believe in the original, like a single kernel generator for everything, or.
I would say you still need to specialize, right? That was like the need. You need to recognize that you don't want compiler to get in the way, in a sense that if your abstraction, your search space don't contain the optimal program, there's no way you can optimize it.
Right.
So you need first to make sure that is nailed, but as soon as that is nailed, then you come back to automation problem.
Okay.
Yeah.
Jacques?
I think this is a difficult one because I think that there are actually so many fun projects. I mean, before Jason said the thing, I was like, oh, e-graphs. Because I love equality saturation, I love e-graphs. I worked with a group on it, but I've just never had a good enough excuse to use it.
Yeah.
And so it's like, oh, more of that, more search. Funny enough, one of the things we were playing around with, I don't know if I should say or not, but like almost like is a Monte Carlo tree search driven, you know, RL driven compiler, you know, which is actually fun, you know, like. But what else? If it is not something I'm doing that I would want somebody else to do, you know, that's a difficult one. I mean, I think it's actually, you know, like there's a lot of opportunities with like the search. ECS, you know, for some reason I feel like there's this linkage between how games are written and compilers.
Like
are like
the entity component action.
Exactly. Where I'm like, why haven't we tried more of that in compilers, right?
I see.
Now, this is a little bit further afield, and I have no idea if it makes sense at all. But, you know, there's always like, oh, this is interesting for me.
Yeah. Cool. Mikhail?
Pretty much what I wanted has already been spoken, like by Jason. Like I also want something that makes a very efficient search on CodeGen. I think there have been many attempts at this. I'm not satisfied with them. Like. Right. I mean, maybe practically they're the best we can get, but I still hope that there is something better.
Phil?
Yeah, I think two answers here. The first one is I'd love a language between Triton and Inductor.
Okay.
Like I think there's a missing layer of abstraction there. It would be really cool. I think there's still times where writing Triton kernels takes way too long and things cannot be expressed well in Inductor.
Yeah.
If you want to be more controversial, I'd say I want a language from natural language to assembly, which is an AGI, and compiler, if you look at it, if you squint hard enough.
Is that ChatGPT?
Yeah. Not yet, but eventually, hopefully.
Okay. Peng?
All right. I don't have a smart answer. And also, I did compiler research for more than 10 years, and I'm a little sick of giving really smart answers. So 2 points. Number one, I felt new ideas come organically. So I would say like engage with users and some ideas will come out. Like flex attention is a great example where if we don't look at how people are writing their custom kernels, we probably wouldn't have come up with that idea. Just practically, we have been thinking about a kind of authoring tool that is on top of Inductor. So we are thinking like, yeah, we already support Triton, and we can use A10 ops, right? So, and maybe there are some other things like maybe compile to the subclasses. So I'm thinking just gradually raise the abstraction level so that it's even easier for other people to write their custom kernels.
Okay. I guess on to the next question. I think many of you, when talking about like why you use ML compilers, kind of brought up heterogeneous hardware. But as I'm sure all of you, like you guys, anybody who's like trying to optimize for heterogeneous hardware, there's often kind of like a conflict between making your compiler work across multiple hardware versus actually getting good performance on this current hardware. I guess I don't need to answer. Like you don't need to answer this if you don't particularly want to. I guess we don't need to like go down the line. But like I guess how do, like to people who want to answer this, like how do you think about balancing heterogeneous hardware performance versus getting good performance on like the current hardware?
I can get that one first. So I think first of all, it's okay to write specific compilers for a particular hardware backend, right? The only question is, what kind of effort you put into it. Yeah. So the way I think about it is, if you, out of box, if you can get about 80% or 60% of the state of art, that's great, right? And if compiler, and on top of that, if compiler is not getting in the way, which means that if you only just stop there and you can do nothing, then you'll be miserable. But if you can just spend additional effort to go for the hardware you care about, you get that 100%. That would be awesome. Yeah.
I think it's a good question. I mean, like I'll mention when we started XLA back in the day, like when we chose some of the ops, we sort of were very explicit with ourselves and being like, listen, we're going to do this. This will actually, in some cases, limit what we can do. Okay. There's a trade
on different hardware, or
on different hardware. It's like maybe this composed op you need on platform A, that composed op you need on platform B. And so there's definitely a question with respect to like portability, right? Like you want, I think actually Jason wrote it really well, whereas like you want a high level of abstraction or operations that you can allow specialization for different hardware platforms. But you also want to be able to have like common ops to give you some of the portability and expansion. So I think definitely customization. I mean, the other thing is tuning, like parameterization. Like if you look at some of the systems folks have built is, it produces something general, but then it gives you the option to then tweak it for different backends.
Yeah.
So, I mean, I think there's definitely trade-offs, and it may change over time, right? What you want today or what you want tomorrow may change, and today you might want to go on one machine.
Right.
Yeah, so I have a cynical take, which is just economics. Like, how much money can you save by focusing on one architecture?
Yeah.
How much money can you save by creating a better competitive landscape and these sort of things?
I see. Yeah, makes sense. Okay, I guess we are at, we will run it into 5:30, although we'll probably go a bit long if you guys don't mind. So I think I have a question kind of for, I guess some of you have kind of worked on ML and through like a long period of time, or like ML compilers. From your perspective, kind of how has the change in ML landscape changed your view on like what is the right thing to do for ML compilers? Like for example, resonance to language models, CPUs to GPUs, kind of maybe like growing scale of like large scale training.
So at least in my end, I think my view changed from building a silver bullet for everything towards something like, have a common infrastructure but quickly specialize to the particular use case.
What changed your opinion on this, I guess in particular?
Because building silver bullet for everything is really hard.
I'm curious whether there was like a particular thing or like a particular hardware change or architecture change that kind of convinced you that building a silver bullet was like not the right way to go.
Let me see. I think the hardware change is more like the evolution of new hardware architecture, tensor core, and so on. Right? These are other things, and also the model evolution, where from the traditional vision-based models to language models, where we really find that originally we think that you are going to build the compiler for 3 years, you are done, then it's going to solve all the problems. Yeah. But then in the end, you find the bottleneck is actually iterating your compiler itself.
Yeah, the hardware keeps on changing.
Yeah.
I think one thing I'd stress is generality is really important, where especially for a lot of like hardware architectures, people look at the models that are most popular today and they build hardware that's really good at running that one model. But I think we're still in machine learning in a really fast-moving industry where things change. If you go back a few years, it would be really hard to predict where we are today. And so I think building generality and flexibility both into your compiler designs and also into your hardware designs is incredibly important.
Okay. I think my next question is, some of you, I think, looking at Mikhail and Peng, have kind of worked both on traditional compilers before working on ML compilers. I'm curious, how do you think that ML compilers differ from traditional ML compilers? I think I'm curious in this question both from two perspectives. One is just culturally, I'm just curious about how do they differ, and the second one is any technical details or any technical perspectives in which you think there's a big differences between traditional compilers and ML compilers.
One very drastic difference for me was amount of performance gains that you can get. With traditional compilers, you get 5% over a year and you are happy, you are overachiever. With machine learning compilers, if you are not getting 2x, then people would choose something else.
Yeah.
And it's very rewarding to start working on machine learning compilers after traditional compilers. Probably the other way around wouldn't work that well.
Yeah.
But you had the other part of the question.
Technical. So I guess maybe that's kind of both the cultural and the technical perspective.
Yeah. So from the technical perspective, traditional compilers, in my opinion, are much more rigorous. So machine learning compilers is just a wild west. Let's just drop half of the values. Maybe it still works. And sometimes it does, and if it does, then people adopt it and start using it everywhere.
Right.
And you're like, that's not fair, but it works.
Okay. Peng?
Yeah, I want to say I was shocked when I first joined the PyTorch compiler team, and I was like, what? This thing is not sound? We're just capturing graph like that? So yeah, I think sound is a huge difference.
Yeah.
And I also think just the pace of innovation is a lot faster. The feedback, in the past we don't get Twitter feedbacks, and nowadays it's always on Twitter. We learn about the complaints or celebrate the wins.
Yeah, people on Twitter don't complain as much about GCC.
That's true. Yeah.
Yeah, I think that's a good point. Although I would say that in traditional compilers, maybe you weren't looking at like the right group, because like at MIT, like this wasn't my work, but like the office next to me had this project called loop preparation. But the idea is in your compiler, you'd go to your loops and you'd figure out, okay, if you skip iterations of loops and just do every other iteration, is the final output of the program still correct? And turns out for lots of programs, you can find some loops where this is true, and it results in great speedups and reminds me a lot of machine learning.
Maybe that code elimination would have solved this too.
Maybe.
Okay. Next question, I think, targeted to Jason and Phil. I think both of you have at various points stated some amount of dissatisfaction with kind of the state of ML systems in academia. If I were a PhD student working on ML compilers, what would you suggest I work on? Yeah. I guess as a bonus question, unrelated to what you work on today. Like as bonus points.
Yeah, I mean, I read a rant about this in my Ask Boss talk, where I think the number one thing I'd say to academics is get benchmarking right, because like you often in these like academic papers you see like clearly conflicting things where like project A is faster than project B, which is faster than project C, which is faster than project A, and you get like a cycle, and it's like clearly this can't be true. And probably 80% of the time we go and try to replicate some academic results, we can't reproduce their results. And sometimes this is misconfigurations where they're like running PyTorch with TF32 disabled, and so their baseline is nonsense. Sometimes they're just running like teeny sizes, so it's entirely overhead bound, and they're just measuring overhead. So I'd say whatever you do, make sure you're doing meaningful benchmarking and measuring something that's valuable.
Yeah. I guess Phil?
Yeah, I think largely the same thing. I think the pressure to publish in academia is very harmful, and can lead to these shortcuts. And yeah, I think more generally, I think people should just be very honest with themselves and publish when they're ready to publish.
Do you think you as a PhD would have accepted this advice?
I published only one paper really. But yeah, I think I was fortunate to have an advisor that let me do that. And I spent like 2 or 3 years just doing engineering without publishing anything. And sometimes I think that's the right strategy.
Yeah, and I will say like another thing, since Phil didn't say this, is I think the review process in academic conferences is really bad. Like one of the biggest travesties, I think, is that the Triton paper was submitted to a bunch of top conferences and didn't get in. And like looking back, that's probably the most influential paper in machine learning compilers in the past 10 years. And it should have gotten to a much better conference than it did.
I guess Tianqi, as kind of like the academic representative, do you have anything you want to comment? Or like perhaps about like how you think like academics have kind of maybe responded to kind of these kinds of issues.
Yes, first of all, I do think and agree that it's important for us to do works that you want to do solid works, right? As a matter of fact, sometimes in my group we also face this similar tension in a sense. We need to build and build solid engineering works in a time that there's also pressure to publishing. On the other hand, I also think that in terms of like evaluating machine learning works and actually machine learning compiler papers or machine learning system papers, I think it's better to have a more receptive view in a sense that in our case, when we read papers, not necessarily reading like, hey, my curve is better than your curve. That's nonsense in a lot of cases, right? It's more like what are the key takeaway insights that you learn from, and if there are key takeaway insights that are helpful, hopefully that is something that the conference audience will appreciate as well. My hope is that there will be more conferences that can be more receptive to these kind of works. What I observed is it's really hard to publish paper, especially if you want to describe like a abstraction or IR, because usually it's really hard to argue your design is absolutely better than all the other things in the field, right? But I think a lot of cases, if you can find insights that people can learn from, I think that's already a good place to go. And in terms of conferences, I think there are, from S+, I find recently I've been more receptive to this kind of works. And MLSys is another venue that I think is a great place for submitting ML compiler related works. Yeah.
Cool.
I think one more thing is, I think we should really encourage people to have more negative results in papers. I think that's one of the root cause of all these issues is you're not really allowed to say that your thing is slower than something else in the paper. Yeah. And I think it's a big issue.
Yeah, that I totally agree. Yeah.
Yeah, I think most of academia kind of has these challenges as well with negative results. Okay, and I guess let's kind of get down to like our final question, and I think many of you have already touched on this. So just kind of generally, like, how do you envision ML compilers are going to evolve over the next few years? I guess I realize that I think you probably can't even predict, what architecture is going to be run in 3 years. But I guess generally speaking, how do you envision that the ML compiler space looks like 3 years from now? I guess we can start with Peng on the other side.
Gosh, you changed the order.
Yeah, mix it up.
Yeah, it's very hard to predict. I'm thinking back 3 years ago. Like, 3 years ago, have we predicted this landscape, Triton and PT2? So I'm not going to predict.
Safe answer.
Yeah, I think it's hard to predict. I think I can tell you a big fear of mine, which is that compilers will become too specific as hardware specializes.
Okay.
And it will become harder to express new ideas, and this will just consolidate model architectures even more.
Yeah. Do you think this is do you think this is primarily going to be caused by compiler writers, or do you think compilers will be forced into it by hardware vendors?
I think a little bit of both. For example, for Triton, everybody hates pointers. All the hardware vendors hate pointers because it's unstructured in memory. But there's programs where you might want to chase pointers for data structures and so on. Yeah. And that's also something I touched on. So, I think if we get rid of this, that's one example of that happening.
Yeah. Okay. Mikhail?
Yeah, I think, in my opinion, all the compilers currently try to find the sweet spot on the scale from how much to abstract stuff from you versus how much to expose.
Right.
Personally, I believe our approach, of course, is the best, but I can see that everyone else probably thinks the same, and rightfully so. And the time will tell. I also think that this sweet spot evolves over time. Maybe what was best when Llama was just released is one sweet spot, but 1 year later, when it kind of stabilized across several variations, and it would be another one. Mm-hmm. But I think it would still be maybe somewhere around Triton, TVM, in this area.
Right. Jacques?
Yeah, so I was sort of saying the bias, of course. The ML part in MLIR stands for multi-level.
Sure.
I believe we will have compilers at multiple different levels. I believe the customization will keep on improving in configurations and adaptability.
Yeah.
So that, in a way, compilers, again, I'm talking as a compiler person, but compilers will disappear because they'll be everywhere.
Okay.
Every part of the deployment stack will have different compilers and graph transformations, things from how you specify it in your model to how you deploy it. You'll have it at multiple different levels. You'll have ML models in the compilers optimizing ML models. I do believe it's actually going to become less of a here is this thing versus it is spread everywhere, and all the deployment teams know how to use it.
Right.
Right. So I'm sort of optimistic about it becoming less and less visible, less and less somebody will complain about on Twitter, X, whatever, as it's everywhere.
Yeah. So you think everybody will kind of become a compiler, or we'll need to kind of become more involved with
I hope we can make it easy enough that people can, but again, I'm saying this very biasly, if I've just seen how folks are using it, it's in many different places, more places they're using it, different levels of abstraction all over the place.
Yeah. This question is intended for people to be more biased about their their views on the world. I guess Tianqi?
Yeah. So build on what Jack said. I think my hope is that we can teach a course or several courses about ML compiler, such that just like people learn about CUDA, system programming, computer architecture, right? Students go and learn about them, they will be able to make use of these tools in their daily life. Yeah.
Jason?
So 10 years is a long time.
I think I said 3 to 5.
Oh, 3 to 5?
Yeah.
Okay, I'm gonna still go with my 10-year answer.
10 years, okay.
So 10-year answer is we reach AGI, and all of a sudden, all compilers are replaced with large language models,
Yeah.
and all of us are out of a job.
Okay.
But machine learning runs so fast because AGI is so good at like hand optimizing assembly and
Yeah, so net neutral.
yeah, net neutral. I mean, we're all out of a job, which is a downside, but
Yeah.
oh boy, it'll be fast.
Okay. Do you have a 3 to 5 year answer too, or?
I mean, maybe we'll reach AGI faster.